Good. And with that, JF, do you want to say anything before we hand it over to Wei?
I think, as usual, I'll be keeping an eye on the chat. I'd say during the talk, maybe post your questions in the chat, and every now and then we'll stop and maybe have any urgent questions. Is that a good plan? And then any longer discussion we'll keep for the end.
Very good.
Yeah.
Daniel, does that sound good?
Yes, sounds good.
Okay, so please, Wei, take it away.
Can you see my screen?
Yes.
Okay. Yeah, I don't think I have a material to present for 1 hour. So if there's questions during the talk, feel free to raise. And I think that's the interesting part. But yeah, first of all, let me thank Daniel and also Jeff and also the rest of the organizing committee for the invitation and also the opportunity. So today I'm going to tell you about the probing the speed of sound and phases of QCD matter with ultra-central nuclear collisions. And so I'll be presenting new results that from the CMS collaboration that's based on a paper we recently submitted for publication, and it's also based on some of the new recent ideas from the theoretical community. So yeah, so to quickly just set the stage, and in relativistic nuclear collisions, and by now there has been overwhelming evidence suggesting that there is a strongly interacting hot and dense matter created. And the most peculiar feature of that matter is that it behaves as a nearly perfect liquid. So namely, it exhibits strong collective behavior with very little viscous momentum dissipations. So despite of a lot of successes, there are still many interesting and important open questions. For example, what is this matter after all? And is it a deconfined state, such as what we call quark-gluon plasma? And of course, probably for many people, this is not a question anymore, right? After all, we have so many evidence that's suggesting that there's such a deconfined matter has been created. I also don't question that. However, I think it's also true that we still don't fully understand what is the exact fundamental degree of freedom of this system. At the quantitative level, is it really as what the theory has predicted, right? It's probably not a system of completely free quarks and gluons. So what's the exact, can we experimentally find out the exact degree of freedom of the system? And what is the nature of this phase transition? And of course, we also, for decades, we believe that... Was it a question? No. What's the nature of the phase transition here? Is it crossover? And if so, and whether there's a critical endpoint somewhere on the QCD phase diagram. And as we know, there's a lot of programs in the lower energy heavy ion collisions trying to pinpoint the possible location of such a critical point. So at the end of the day, so to address all these questions, it boils down to whether we can experimentally directly constrain the equinoctial state and over the entire QCD phase diagram. So the equinoctial state is a thermodynamic equation that relates state variables. For example, it can be an equation that relates three thermodynamic variables, such as the pressure, volume, and temperature. And the simplest example is the classical ideal gas, and that's kind of the first thing we've learned in the statistical mechanics class. And for the for the black body system, such as the system of photon gas or the nearly massless particles, there are various ways to express the equilibrium state in terms of the energy, volume, temperature, pressure, the entropy. To determine the equilibrium state, for example, if we want to determine the free parameters in the equilibrium state, what we usually do is that we keep say a third variable fixed, and let's say we keep the volume fixed, then we can measure the variable 1 versus the variable 2, like energy versus temperature, then we can determine this parameter. So in QCD, the equilibrium state of the hot QCD matter has been a subject of interest for many decades, and there has been tremendous progress made, especially by lattice QCD, in determining the equilibrium state of QCD matter near zero barochemical potential. So as shown here, this is the lattice QCD prediction from the hot QCD collaboration for the pressure, the energy density, and entropy density as a function of temperature, where it has predicted the deconfined state of matter at high temperature. Specifically, it predicts a rapid increase of the degree of freedom of the system, and at high temperature, we asymptotically approach this so-called ideal gas or non-interacting limit. So the question is whether we can experimentally direct test it and verify that. We do believe in lattice QCD, but it would be nice if we can actually put experimental data points directly on plot like this and compare with the quantitative prediction of lattice, right? And as I mentioned, to constrain the equilibrium state, what we need to do is to measure two thermodynamic quantities at one time and keep the third one fixed. For example, we can keep the volume fixed, and if we can measure the entropy, density, and the temperature, then we can directly compare to this calculation. However, the difficulties in heavy-ion collision is that all these thermodynamic quantities, pressure, energy density, entropy density, and temperature, and so they all rapidly vary at the function of time. So they are not fixed. So extremely challenging to achieve what we hope to achieve. And for example, we've seen a lot of measurement of temperature, right, with various probes. And we know there's a lot of evidence we have a system of temperature of 200, 300 MeV. But to really direct probe equilibrium state, we have to measure another quantity that corresponds to that temperature. So that was the challenge. The speed of sound is one way to directly probe and constrain the equilibrium state. Is defined as the derivative of the pressure with respect to the energy density at near zero chemical potential. It is interesting also because experimentally sometimes it's easier to measure the change of the thermodynamic quantities rather than the absolute value of the thermodynamic quantities. And another reason that we are interested in speed of sound is that there's a well-known phenomena that if the object moves faster than speed of sound in a medium, it's going to excite the shock wave, also called Mach cone, and something that we're also actively looking for in heavy-ion collisions using hard probes like the JETS interacting with the medium. So this plot shows the lattice QCD prediction for the speed of sound as a function of temperature using 2+1 flavor. And as you can see at the very high temperature, so the speed of sound will asymptotically approach to the ideal gas limit, which is 1/√3. And an interesting feature of the speed of sound is that around the phase transition temperature, the crossover temperature is going to reach a minimum. So if we can locate this minimum and determine the minimum value of the speed of sound, So that information can tell us about a lot about the nature of the transition. For example, for first order phase near first order phase transition, the speed of sound will significantly suppress and toward 0. Experimentally in heavy ion collisions, in terms of the constraint on the speed of sound and the equilibrium of state, and there is this well-known Bayesian analysis that was performed back in 2015, where as you can see here, using the experimental data with the theoretical models, we can provide a pretty good constraint, direct constraint to the equilibrium of state. Although there are still sizable uncertainties, and the uncertainties is still fairly large, not yet competitive to the theoretical uncertainty achieved by the lattice calculation. And these uncertainties is partly because to improve this uncertainty, you can, of course, measure the data much more precisely, or we can also look for new observables that may provide better sensitivity to constrain the equilibrium of state and speed of sound. That's the approach I will talk about. The later is the approach I will talk about in the rest of my talk. And also to mention that in the most of the more recent Bayesian analysis, that the equilibrium of state usually take lattice equilibrium of state as an input to constrain the uncertainty of other observables, and we don't directly try to constrain the equilibrium of state data-driven way for reasons I mentioned here. There has been also wide interest in the sound wave propagation within the strongly correlated systems in other areas of research. For example, called atoms. When you tune the system near the Fishbach resonance, it's a strongly correlated system, and studying the propagation of the sound waves and provide a lot of important information about the property of the system. For the closed and dense QCD matter, another corner of the QCD phase diagram, there's also an important question: what is the state of the matter inside neutron star, and that we suspect that's the very dense QCD matter. And by measuring the mass and the size of neutron star, so that can put a direct constraint on the equilibrium of state inside neutron star, which at the moment still have a large uncertainty, as you show for this is one example from a recent paper. Okay, so how to improve the constraint on the equilibrium of state, and specifically the speed of sound. This is the topic of my talk. So I'll start from this work back in a few years ago, and which kind of motivated a serious work subsequently. And this from Fernando, Giuliano, Matt, and John Eve, and some of them actually are here. So if you have hard questions related to this, then so they can help to answer. So simply speaking, what was done in this paper is that they used two very simple experimental observables plus hydrodynamics to put a direct constraint on the QCD equilibrium of state at high temperature. And more specifically, what was done is that you can take the total entropy and total energy of the medium that created in heavy ion collisions at the freeze-out, and run the hydrodynamic backward and pull this amount of energy and entropy density back into a hypostatic system or effective system. It's a fluid. It's a static fluid system. It has a uniform density, and with some effective volume and temperature. So this volume and temperature will be different from the volume and temperature of the initial system creating the heavy ion collisions. So you can establish that connection through these mathematical relations here, where the energy density and entropy density are related with the temperature through the equation of state. So that's how the equation of state comes into play. So you have two equations that are two unknowns. You can solve them. You can solve them for different equation of state, and then compare to experimental data. So comparison to the experimental data is through the fact that the entropy is is proportional to the total number of charged particles produced. And this temperature, effective temperature, I will mention, I'll talk a bit more later. And it has been found through hydrodynamic calculation that is roughly the average PT of the charged particles divided by 3. Now, if we accept this relationship, and then we'll find that the speed of sound, you can through the thermodynamic relations, you can show that the speed of sound will be related to the derivatives of the log min pt respect to the log of the n charge. So basically, we are looking for a relative change in the min pt respect to the relative change in the charged particle multiplicity, which can provide us directly provide us information of the speed of sound at the temperature of this T effective, the min PT over 3. So this was done in
Okay.
the. Yes.
Do you mind if we take a question now?
Sure, go ahead.
Uli, you have an urgent question?
Yeah, I'd like to ask this before you move on because I might otherwise get lost. So
Yes.
this red equation T effective is proportional to 1/3 of PT. The average PT over 3 is measured in the experiment. So it's at or after freeze out, at the point of freeze out. T effective, you argued or explained before, is obtained from taking those freeze out data from the experiment and using hydrodynamics to back extrapolate to some point where I'm not quite sure to how far you back extrapolate. So in other words, this red equation seems to have information from two different times in the evolution. How do you correct for that, or how do you take account of that?
Yeah, so let me try to answer, but Zhang, you can also chime in later. So I think to back extrapolate maybe not the exact right word. It's not back extrapolate in time, but it's more like put this energy and entropy in a new system. It's a static, the uniform static fluid system. So this system has a total energy of and the entropy of the values we observed at the freeze out of the original system. And this system has a new volume, a new temperature. And
but you want that system to be a QCD system so that the temperature that you extract from that trick is actually a temperature that you can somehow connect with the plots that you have shown before from lattice QCD.
yeah.
So how do you define this physical system that is characterized by V effective and T effective?
So how T and V are determined? So right, the T and for example here, the T and energy density are related to through equation of state. So actually, so the T effective is found to be weakly dependent on the equation of state. It's always roughly around 1/3 of the average PT. This is just because from the dimension, if you think about maybe min PT is like the average energy, and the temperature is roughly a third of it. So effective temperature is always roughly a third of the average PT, and then how much energy you have. Then you based on the relationship between temperature and energy or entropy, then you determine the equilibrium state at this temperature.
Okay, so let's see. Since we have time, I mean, it's not necessarily a bad thing to take a moment. If you don't mind, wait, take a
Yeah,
moment.
no, I think it's important. Actually, this is important. We are clear on this. So feel free to, you know.
So I'll go with Bernd first, and then we'll come back to the one in the chat. So Bernd, go ahead.
Yeah, thank you. So I confess I'm also a little puzzled by these two equations. It is true. So at freeze out, we have a common understanding that part of the motion of the emitted hadrons is due to thermal motion, and part of it is collective flow. I mean, that's the fundamental to the paradigm by which we interpret these events. Now, the kinetic energy in the collective flow contributes to the energy of the system, no question. But normally, we argue that it does not contribute to the entropy of the system because it is collective. It is not random. And so the collective motion in itself should not carry entropy with it. So in other words, I understand in some sense the first equation, but I don't really understand the second equation because I don't know how to subtract the non-entropy carrying collective flow from T effective. Could you say something about that?
I'm trying to understand. So at the freeze, we measure the total number of particles at the freeze out. So if the entropy is conserved all the way from the beginning, so that provides us the information of the total entropy produced initially, right? So are you arguing that there's a change in the entropy? The entropy is not conserved?
No, absolutely not. All I'm saying is the transverse momentum at the end has contributions from an entropy containing effect and from a non-entropy containing effect. And so I don't know how to disentangle the two in order to get an effective temperature.
But I think the non-entropy effect, namely the collective flow, is exactly what determines the sound velocity. That's why the velocity of so it's true. It's because it's the pressure wave. It's how the system reacts to if you increase pressure and energy density. It gives this hydro flow, and that's exactly what is determined by the speed of sound. So this non-entropy part determines the speed of sound. Isn't that?
That's right, but that
Let's
doesn't mean that T effective basically means that I assign the effective temperature with entropy.
But
T effective.
But T effective has nothing to do with the original system.
Okay, let's see. We may have to defer some of this to later. Thank you, Bernd. Actually, Jürgen, you had a question about the mean PT. Maybe let's get that out of the way, and maybe we'll defer further questions later.
That's about the accuracy at the end, about how well you actually can map via this hydro mapping the T effective. And the reason, so the question is, we know that the PT spectra are not perfectly well described by hydro. And therefore also the average PT is not perfectly well described by hydro.
Yeah, from my own experience, I'd say mean PT is not so bad because at 0.5 GeV, it's not that difficult to get a mean PT of pions, right?
Okay, my question was actually, what is it? The error is about 5%, 1%, 10%. That this non-hydro tail introduces in the T effective, because at the end there will be an error bar. So my question is, how big is the error bar coming from the difference?
A typical hydro fit, how well would it fit the mean PT? I'd say a couple percent. I leave some of my colleagues add comments in the chat if they disagree, but I'd say 5% would be typical for the pion mean PT.
Maybe one should be more quantitative.
Yeah.
I can answer that actually.
Oh, go ahead. Yeah, go ahead.
Let's say in your environment, when you calculate MPT by cutting off the part of the higher end of the spectrum from all the way to around 5 GeV, still it has almost no effect on the result I will present. And of course, if you go further, closer to 3 GeV, then it start to have an impact. But let's say you exclude everything above 5 GeV, it has almost no effect on the measurement.
Okay, I'd say let's keep going, and maybe we can come back to some of the deeper questions later in the discussion.
But thank you for all these questions. I think that is very, very interesting to have this discussion. Yeah, so this basically what they have done. You can to calculate this change in MPT and change in charge. All you have to do is to take the MPT and dn charge data measure at two different energies by at least, and plug in those equations to calculate the speed of sound. This is what they have derived with the uncertainty. Here you can see that I think there are two limitations here. The ones the larger uncertainties. These are mainly because they come from data themselves. There are two energies. The uncertainty are independent from each other. And the size of uncertainty is also not so different from what we previously obtained from the Bayesian analysis, which I don't think is a surprise because if you think about the information you use, right, hydrodynamics and similar set of data, we should arrive at similar conclusions, right? There should be similar level of constraints. Another limitation I think is that it uses the energy dependence of MPT and uncharged, and these are not really unique in AA collisions, right? Because MPT and uncharged also increase with energy in PP and E plus and minus, but we wouldn't interpret that as the change of the temperature entropy density. So how to improve this? Before I talk about how to improve that, let me make a comment also on this effective temperature, but we can also keep discussing that later. There are actually a lot of questions, a lot of debate on what is effective temperature is. I want to first comment that what it is not. First, it's not the result temperature that we extract, using blast wave phase or using thermal phase. And because it also this effective temperature also includes the kinetic energy of the system and or the radial flow. It's also not some kind of time average temperature that we obtained, let's say from photons, the feeding photon spectrum. So what is it? So this temperature will be the initial temperature of QGP if, at least to a good approximation, if the total energy is conserved all the way to the freeze out and is 100% measured by the experiments. However, in reality, practically, usually there's only a slice of the QGP fluid we measure, and the system is built in with some longitudinal expansion that this longitudinal pressure will do negative work that will cause the energy to leak out of the system that we measure. So at the end of the day, so this temperature should be considered as some kind of initial temperature, but or lower limit of the initial temperature of the quantum plasma. And as I mentioned, it's been found from hydrodynamic simulation that it is about, to a very good approximation, is about a third of the average PT. Doesn't matter, experimental. So to relate MinPT with temperature, actually, there's already work in the 80s, for example, from this paper from Liao Van Hoff, and to probe the eternal state and the possible phase transition. And of course, at the time, it's still kind of qualitative. It's not related to the hydrodynamic simulation. But you look at the here is if you have a sharp first order phase transition, this is what he predicted, and but in reality, If you have not fixed impact parameter, the curve may look more like this. But I think some of the qualitative features already is very similar to the idea we are talking about today, that the mean PT grows with DMD data. So keep this in mind. And so I will come to the part of this, the measurement I will present how to use ultracentral nuclear collisions to precisely constrain the speed of sound. I'll have a quick reminder about the concept of centrality. So centrality is the control of the impact parameter, the system volume, and system geometry, as most of us know very well. Experimentally, they are determined by usually the final state total energy or total multiplicity, and most of the time they have very good correlation with impact parameter. Up until a certain point, when you go to extremely central, at some point the impact parameter cannot be reduced anymore because it becomes zero. The system size cannot increase any further. At that point, we could still get the total energy and entropy that's deposited in the system can still fluctuate to larger values. And so those are the kind of the rare events. Those are what we'll use, what we call ultracentral collisions, what we will use to try to constrain, to determine the speed of sound. Actually, there's an earlier paper from CMS to study the anisotropy flow in these ultracentral collisions, where we have shown that indeed the system geometry seems to be stopped changing once you pass beyond, say, top 1% in centrality. So the idea using the ultracentral events is first proposed in this paper by Fernando, Jean-Yves, and collaborators. Basically, the idea is the following, right? So when you look at the not very central heavy-ion collisions, when you go toward the central events, you are making a bigger and bigger coagulum plasma with relatively fixed temperature. The temperature remains constant. And until the system becomes, the impact parameter becomes nearly zero, then you can't make the system bigger anymore. The volume reaches maximum. But beyond that point, you can still require higher charge multiplicity produced. And beyond that point, you'll be making a hotter and hotter QGP with a fixed volume. So the expectation is that beyond that point, the entropy density of the system will increase and the temperature of the system will increase. And based on the relationship between the increase in the mean PT and the charge multiplicity, that can provide us direct information of the speed of sound. So this is the slope. Basically, this is the relationship of the equation to the speed of sound, right? So this is more non-trivial prediction by hydrodynamics that has not been measured before, but it's still on a relatively simple observable that could put direct constraint on the equilibrium state, and this is what we want to try to measure. So I will be brief on the CMS experiment. So this is a nice event display of very central light collisions in the CMS detector. Generally speaking, CMS was designed to handle this type of events very well. And so in this analysis, the main detector uses the silicon tracker, which has the coverage of 5 units in pseudo rapidity. And we also use a forward harmonic calorimeter, the HF, as a centrality estimator. And we have also used a 0-degree calorimeter in the very forward direction to mainly reject the pileup events. So actually, using CDC, we're able to obtain a sample with very high purity and free of pileup events. So here, let me go through how the measurement is done. It's actually relatively simple. here we use the for HF as a centrality estimator, the energy in the total energy in HF, and then we use the mid rapidity of the tracker for the particle of interest to measure the average PT and the N charge. So basically all the information is just in this one plot actually. So here we plot in the y-axis the PT spectrum of the particle of interest. On the x-axis is the event total HF sum transverse energy. So in CMS, our spectral measurement has a cutoff at around 0.3 GeV. So from this plot, what we do is we take each HF ET sum bin, and we look at the particle of interest PT spectrum within mid rapidity and PT greater than 0.3 GeV. We apply all the efficiency corrections, and we also perform extrapolation to 0 PT. So we need to get a full spectrum. There is one subtle effect that I want to mention here is that there's our efficiency has a slight dependence on the detector occupancy, say over 5% centrality. So that effect we have to calibrate that effect carefully and correct for that, because we're looking for very small change in the shape of the PT spectrum or the average PT. So once we have the fully corrected spectrum, the mean of the spectrum give us the mean PT, the integral of the spectrum give us the total N charge, and we do this in every bins of HF sum ET, and we plot mean PT against the N charge from all the HF bins. To do the PT extrapolation, we use the Hadron function. This has been yes.
Wait, do you mind if we ask a quick question about the previous slide? Jean-Yves had a question about the selection.
Right.
Yeah, my question is just what was the reason for just only keeping between minus 0.5 and 0.5 where you have minus 2.4 to 2.4? Is there a specific reason for that?
Yeah, so the main reason is that the tracking performance is best near mid rapidity. So the systematic is better. It's a balance of the systematic and the statistics. The systematic can be controlled much better near the mid rapidity.
Okay, thanks.
Yeah, for that reason, we decided to stick to mid rapidity. The PT extrapolation is done using a Hadron function. So this function has been used by Alice quite extensively. And for example, we test it using the models, the Hydroid, and it can pretty much reproduce the true mean PT of the spectrum within the 0.5% level. The conclusion is similar when we test other generators, such as the trajectory, using trajectory PT spectrum. So in the end, so this extrapolation contribute to about 4% of systematic uncertainty on the final extracted speed of sound in the data. Then I'll explain how we do in a moment. Just here a few remarks at this point. As I mentioned, I want to emphasize to have a full PT coverage is required, because otherwise the speed of sound you extract will generally be smaller. The phase space for the speed of sound extraction or the particle of interest and the centrality estimator is important to have them separate in rapidity. Otherwise, there will be a bias effect, which we can discuss also later. The total energy centrality estimator is generally better than the multiplicity centrality estimator. Again, we can also discuss it in detail later, because this can help to eliminate some multiplicity fluctuation effect. So in the end, the last point is I want to particularly emphasize to use a self-normalized observable. This is really the key to beat down most of the systematic uncertainty. So therefore, in this work, the observable that we are going to use will be not just min PT, but min PT normalized by some reference min PT, and the charge multiplicity normalized by some reference charge multiplicity, and the reference value we chose them from the 0 to 5% centrality. So this will help a lot to cancel most of the systematic uncertainty. We still measure the min PT in the reference bin because we need to estimate the effective temperature. And so therefore, yeah, so there has to be uncertainty that associated with absolute average PT. Okay, so let me first show you. Yeah.
A quick question. When you say total energy, you mean total transverse energy, ET, not, or you mean total energy?
So
It's
which one?
EP. If you say here total energy of multiplicity instead of multiplicity, you mean total transverse energy.
Transfer, yes, yeah.
Yeah, okay. Just.
Yeah, produce energy.
Okay.
So where does the total energy enter in these observables that you list there in the box?
It doesn't enter directly, but it's used as the centrality estimator, used as the handle to vary the centrality. But we don't, so it doesn't enter into the final observable. The final observable is only use the information in the mid rapidity. So yeah, so it's basically we want to decouple the observable of interest and the centrality estimator, as we do in many measurements. Otherwise, there could be the bias effect.
Okay, thank you.
Yeah, actually, it's actually also an important point we can discuss later. Let me first show you some predictions that we obtained. So these are really predictions that the authors have not seen the data when we requested this. The both from one's from Trajection and the other from Gardin et al. So both are hydrodynamic models and both use lattice QCD kernel state, but there are lots of difference in details, right, as we know. And both they have qualitatively predicted this cartoon that we showed earlier. If you remember, it's flat and then rise, right? It predicts there's a significant increase of average PT toward outer central event. And the slope is actually similar. Maybe the trajectory has a slightly steeper slope than Gardin et al. And what's the difference is that there's a dip around here, this normalized uncharged 1.05. There's a dip that present in the trajectory model, but not in Gardin et al. And the origin of this, I have some speculation what that might be, but it's not entirely clear. We have not pinpointed one effect that causes this dip. But it's in trajectory models, so therefore it's probably not some very exotic physics. We just have to figure out with some more detailed studies. Okay, so now let's look at the data. So this is the data that overlaid with the theoretical predictions that are shown in the previous slide. And for the normalized min PT versus normalized multiplicity. And you can see the uncertainty extremely small. So we are looking for only a couple % increase of in min PT toward outer central events. But we were able to get a very precise measurement because of the self-normalized variables. And in the data, we see a similar significant increase of min PT toward outer central events, just as the model predicted. If you look at the slope, qualitatively, the slope is well, okay. So first, there's a dip is also there in the data. That's correctly predicted by trajectory model. Now, besides this dip, if you focus on the slope of this rising part, the slope is similar between data and the trajectory and the Gardin et al. Model. Maybe again the trajectory slope maybe slightly steeper. Yeah, so I bring back this small cartoon just to illustrate what's happening. So initially, and not very central events, we are making bigger and bigger QGP with constant temperature. And then once we pass impact parameter to 0, we start to make a hotter and denser QGP with increase with a fixed volume and with increasing entropy density and the temperature. So that fulfills our requirement of keeping one thermodynamic quantity fixed and measure the change of the other two to determine equilibrium state. So to extract, how do we extract the speed of sound? So we perform the fit to only the high multiplicity part of this distribution using a function that's shown here is kind of a power function, but not exactly. It has this term. These are crazy term that's here, which so this term is here is to account for the transition region. You see this transition region. So how fast it turns from a flat to a steep rising. So how steep this curve will rise will depends on the multiplicity fluctuation around zero impact parameter. So if the multiplicity fluctuation is large, and this transition will be shallower. If the multiplicity fluctuation is very small, then the transition will be steeper. So basically that's why there's this parameter n charge E and sigma. This is the average multiplicity and the fluctuation of multiplicity at B equals to 0. These are the model, of course, model dependent fit parameters that will enter into this fit. But to minimize the impact of these parameters, we try to only fit the high multiplicity end of the distribution, and from there we also have a systematic uncertainty that is associated with the choice of the range that we perform the fit, and in the end this is the value that we have determined for the speed of sound square about 0.24 plus minus 0.016 systematic uncertainty at a effective temperature measured by the average PT over 3, about 220 MeV.
Wei, if you don't mind me asking, it sounds like you're pretty far from that knee. Shouldn't you be able to just use a straight line? I mean, a straight exponential or power law?
Yeah, it's very close. It changed a little. It changed numerical, still changed numerical value a little bit. We try.
Are we talking about 1%, 0.1%, 10%?
Oh, I think it's few percent.
2%. Okay, so it's not
few percent effect. I don't remember exactly, but it's not just a couple percent.
I see. And the sigma and the knee, are those, do you fix them?
So right, let me come to it. That's in the next slide.
Okay, very good. Go ahead. Sorry.
Yeah. So these two parameters are fixed. They are not different. They can be fixed.
If you're discussing that already, it would be instructive to see how this curves, the shape of the curve looks like at lower end charge, even if you don't include it in the fit. You have to have such a plot. So you just fit up there, but then you extrapolate this curve. Presumably it doesn't have a dip, does it? It's flat.
This curve will not have this curve will
no, the black curve.
So this
yeah, that is your fit curve.
Yes, curve, if you extrapolate, it will look like the Gardner et al. Model. It will not have a dip.
Okay, so it will look okay. So it will not follow the data very well below.
Right, it will not because
another 1 or 2 points. Okay.
Right,
okay.
This dip is not. It's very on this scale is small, but it's very significant, and it's not predicted in the original model. Yeah, so that's why the fit cannot. So I think ideally the the farther we can go, if we can afford the statistics, we just use the very high end of the uncharged and to stay farther away from the deep, the better. But of course, we also run out of statistics at some point. So we choose a range that sufficiently away from that, and we estimate uncertainty from the potential impact by the imperfect description of this function influenced by this structure.
So Zhang, you had some questions, but if you have information on the next slide, maybe we'll let you finish the next slide and then we'll come back to the questions.
Let me finish this slide. Yes, this slide tells you how we determine the uncharged knee and sigma. So they can be determined independently just using the uncharged distribution that we also presented in this paper. And also it's measured very precisely. So yeah, the idea is also in a paper that where Zhang Yi is an author to you model the multiplicity distribution at a fixed impact parameter using some Gaussian distribution. And then you convolute this Gaussian distribution at different impact parameter to try to model the full distribution of the uncharged multiplicity. And then you can perform a fit with the data, then you can determine the mean and the width of the uncharged distribution at a fixed impact parameter. So that's what we have done. We follow the exact recipe in this paper, and the value we extract here, the uncharged knee is 1.1 times the uncharged for 0 to 5% centrality. Sigma is about 2.7% of the average multiplicity in 0 to 5% centrality. So about 2 or 3%, this width, 2 or 3% relative multiplicity fluctuation. I should also want to point out that this distribution is measured, is not directly you plot uncharged distribution at mid rapidity. So it's done still similarly, it's done by you vary the centrality using HF, and for each HF range, we look at the average uncharged in that HF bin, and then make this distribution. So some of the multiplicity fluctuation effect will come play differently from if you simply plot uncharged distribution from mid rapidity directly. If there's question, we can maybe this is good moment too.
I didn't see, well, if people have questions, you can raise your hand. I think most, I've had questions, but I think they were answered.
Okay.
I do have one actually. If you go on the previous slide, I guess the part I don't understand is the formula for the speed of sound in terms of the log of the multiplicity, log of the charge hadron. Doesn't have anything about the knee. Why do we suddenly need to know about the knee?
Because if we get closer to around the knee, this curve will bend, right? It will not be a parallel. And so how much this will bend toward the knee is modeled by this. So if the sigma is small, then what should happen is that you have a power, and then rapidly it will turn into a flag. So if this sigma is large, then what you will see is that this term will gradually turn over and become a flag. So,
but you said that the C squared would be different by how much if you forget all that and just use the thermodynamic relation. You said it's 2-3% only.
A few percent.
A few percent. So all what he's discussing is a few percent correction to the speed of sound, but
Okay.
It's probably within the systematic error.
Okay.
Or slightly bigger only.
Let me precise. If we still, you have to fit for uncharged, normalized uncharged above 1.14. So you still have to fit a high multiplicity part. Now, using this equation or simply a straight line or simple power function differ by a few percent. But we cannot extend the fit all the way here because the function will not fit.
Okay,
Because the dip will not describe by this function.
sounds good. All right, please feel free to go ahead.
Yeah, we will have to fit as high intercharge as we can afford statistically. This is, I think, let me see. This is not the right slide. So, sorry, I have to. I just found for some reason. Some of my updates were not in the slide. You can still see my screen, right?
Yes, yes.
Yeah. So round two. Now we have a temperature. We have the speed of sound. So we can now put a point on the map of the the equinal state, right? I said that was a goal I mentioned earlier, and you can see that here is the blue, the green box is this is from the Nature Physics paper from Fernando Johnny et al. Originally, and the red box, this is our new measurement where you can see the precision has been significantly improved. I would imagine that if we take this data to run a Bayesian analysis, we should arrive at a similar conclusion, although through a different approach. This kind of blue bar is directly fitting the trajectory result, which is still consistent with lattice, but has somehow larger uncertainty. We can discuss that later, where that may come from. So in general, we conclude that the data are in good agreement with lattice QCD prediction where a deconfined phase is predicted. Okay, so I want to end the talk with to discuss some questions that are being debated. So the first is whether this slope is indeed respond to the speed of sound. And this was actually looked at by the trajectory authors. And in this paper that they posted recently, they try to correlate the extracted speed of sound with some parameters that they vary in the lattice equinal state. And they seem to find some correlation, but it's inconclusive because the problem is not so easy to dramatically change the equinal state without messing up many other observables. So there are more studies ongoing. And of course, if we completely change the equinal state, the very different equinal state from lattice QCD prediction, that would also have been excluded by other observables, right? So if you don't care other observables, I tend to believe that this slope will respond to the speed of sound. But we will see whether that's the case. Hopefully soon. There are also questions, what else can impact the slope? There are three things I want to talk about. The first one is the impact of the low PT cutoff of the spectrum. So if you have a lower PT cutoff to the spectrum, that will obviously impact the slope. So we have a result just obtained with mean PT just above with a PT cutoff of about 0.3 GeV, where you can see that the slope is reduced. This is true for both data and theory calculations. So it's not valid anymore if you extract the numerical value of speed of sound when you have a PT cutoff. However, you can still compare to the theoretical models, and the conclusion should remain the same, that the slope that we observed in the data is comparable with the theory predictions if you focus on the very high multiplicity range. And actually from here, because without PT extrapolation, our uncertainty becomes even smaller, and you can actually start to see that trajectory slope, it becomes it's more evident that it's larger than the data. Well, the Guardian et al. Slope is more similar to the data. the choice, there's also argument that the choice of centrality estimator will also impact the extraction of speed of sound. I would say that is both right and wrong. We do have to be careful to choose the appropriate centrality estimator. And once we do that, then I would say the conclusion remains the same. For example, one study that we have performed here is that instead of the default HF-based centrality estimator, we use the forward tracker, the forward region of tracker from eta 1 to 2.4, to use this forward charge multiplicity as a centrality estimator and repeat the whole analysis in the same way. And here you can see how they compare to each other. The red is still this is the default result. The blue now is obtained with this new centrality estimator. Now they are different. Well, first off, the deep structure becomes less evident with this multiplicity-based estimator. That's why I suspect this deep structure might be related to the multiplicity fluctuation in some way. However, if you look at the very high multiplicity part of the distribution, the slope that obtained actually, and therefore the extracted speed of sound will be very similar. They will be largely independent of the centrality estimator between these two of them. The last one is the modeling of the initial energy and entropy deposition. These actually, so as we know in the Trento initial condition, the entropy deposition follows these this function, where many models took p equals 0, which essentially follows square root of the TATB scaling. In that scenario, in this paper has been tested that as you go to more and more central collisions, the system size doesn't change. The radius change very little, maybe only by less than 1%. So the assumption for extracting the speed of sound is valid under this scenario, that the system size remains fixed, right? However, in the trajectory model have introduced a new parameter for this is energy deposition. The energy deposition will be the 4/3 the power of 4/3 of the entropy deposition. There's extra free parameter of Q. So if Q equals to 4/3, it will be the same as the Trento initial condition. But in the trajectory model, this is a parameter that can change. If this parameter, if the Q is large, it can start mimicking the unpole scaling of entropy deposition, meaning that the system is more effective in depositing more entropies when the nucleons are all in a smaller area, more closer to the center. So in that case, when you have a large Q value, then your system will become effectively smaller and smaller as you go to ultra-central collisions. And then that assumption that the system is fixed is not valid anymore. And that is likely to be part of the reason that we see there's a large uncertainty in the slope parameter extracted out of trajectory. And some of that is related to the fact that the Q is varying. Sometimes it's allowed to have a larger value, a lot larger than 4/3. Again, the more studies still ongoing to understand. This is, of course, the key assumption in the whole scenario. So a little bit on the future. So what's next, right? So we have measured currently at one temperature using one energy. So in principle, at the LHC, we have 3 different energies. We can apply the same analysis to extract speed of sound at 3 slightly different temperatures. We may even explore the extrapolability dependence because there will be a few % variation of mean PT over pseudo rapidity of 2 or 3 units, and that's a lot already, because we are looking for here a couple percent variation in PT. And maybe in the future we can also run LHC at different energies, maybe at injection energy. So we'll see whether that can happen or not. What's more interesting is that I will be very interested if, for example, STAR can look at this at lower energy. There are multiple data at multiple energy collected, right? If we can apply this approach and try to extract the speed of sound as a function of temperature, and maybe even see some monotonic behavior, that will be really a clear signature of some kind of phase transition is happening. But of course, there could be complications there, because the speed of sound at finite baryon chemical potential may also receive contribution from the net baryon densities. And this is a recent work from Fernando and the collaborators to look at the small system in P-lab collisions, where you create an even hotter quark-gluon plasma with drastically different size, much smaller size, where they look at the mean PT versus DND eta, and compared to the ALICE data, they agree very well. But what happens if we push to also ultra-central P-lab collisions, whether this rise also happen, and can we extract the speed of sound using that at different effective temperature? So that's also something very interesting to look at in the future. So to summarize, so in this talk, I presented the measurement of a new hydrodynamic probe, which is the average PT versus the N-charge in ultracentral lilac events, which provides unique sensitivity of constraining the equilibrium of state of the QCD matter. We obtained a precise extraction of the speed of sound square about 0.24 at effective temperature around 200 MeV. And this is in good agreement with lattice QCD prediction at μB near 0, providing direct evidence for deconfined phase of QCD matter at high temperatures. And the future
PT was 3, not PT, right?
I'm sorry. Oh, sorry. Yes, me also. That's right. And future measurements at other energies and in small system in comparison with theoretical models will be very promising to map out the QCD phase diagram. Thank you.
All right, thanks a lot, Wei. I think there's a few questions. Let me alternate between, maybe we can alternate between questions that have been asked in the chat and people raising their hands. Uli, you had a question. You asked the first question in the chat early on about chemical equilibrium. Do you want to start?
Yeah, maybe if you just go back to 2 slides to page 33, where you speculate of what might happen when you extend to BES energies. You mentioned that the speed of sound there doesn't also gets corrections of finite net baryon density. But I think what may be more important is that below TC, it's known that the system goes out of chemical equilibrium. And so the system may be still describable by a temperature, but no longer by a chemical equilibrium state. And then the speed of sound for the non-equilibrium, chemically non-equilibrated state as a function of temperature looks different than what you have indicated there.
Yeah, I agree, and that is something probably impact all everything we want to measure about the phase related.
The analysis will be much more complicated because you somehow have to find in experimental information that allows you to correct for the chemical non-equilibrium situation below TC.
Yeah, I agree. Probably there will be a lot of complication, but if we can just try to see how much we can push down here, if we can see some dependence that whether it follows the lattice prediction, that's already interesting. Maybe it's not trivial to see the minimum.
Jürgen, do you want to go ahead?
So first of all, about lower energies. I'm afraid at lower energies we are completely dominated with fluctuation, so you cannot actually make this measurement at all. We know at the SPS, those of you who still remember the Jape psi measurement of NA50 in the tail, which was very, very dramatic, but very wrong because it was all fluctuations. You have to go to a fraction of a percent, and that at lower multiplicities is very difficult, in fact impossible, unless you have a huge detector, and even then it becomes difficult. So one has to see exactly where it goes away. I'm not even sure how well it could still be done at injection energy. One has to look. Maybe that's still okay. Maybe the upper rig might also still be okay, but you need a huge detector because you have to select fractions of a percent in order to be not dominated, in order to go into this region where the area is constant. And then you have your fluctuations have to be small compared to that. And
So you're talking about finite number statistical fluctuations?
Exactly.
Not thermodynamic fluctuations.
No, just it just becomes impossible to fix centrality better than a 1-2% just by fluctuations of the. And for that already you need big acceptance. You might still remember the NA, the ones who tried it once was NA38 going into the tail and looking at the Jape psi, and that was then found to be really only fluctuation dominated, and then nobody looked at it up till the LHC. Never, the smallest centrality bins were 5%. So that's one thing. But I have a second question to Wei. A natural suspicion one would have is if you go in the tail, where you start to exhaust the number of partons which can collide, is that you bias yourself a little bit towards more high PT hard scattering, which both would give you a little bit more N charged and a little bit more PT. So have you, I mean, I know actually it's not the case, but have you also checked that the PT increase in the tail has nothing to do with hard scattering in the data? Have you checked that?
The PT increase in the tail.
Yes, because that is would be the first suspicion. And
right. So I mentioned at the beginning that we check, for example, if we cut at 20, 10 GeV all the way to 5 GeV, it will has basically no effect to
yeah, that's not necessarily so.
So what
okay.
else
But
we check?
I mean, so we checked it, and the outcome is clear. So what you can do is you can make the ratio of the PT spectra, and then you are much more sensitive to any hard scattering, because we know that would then the ratio would increase at high PT, and the higher you go in PT, the higher the ratio would become, and that's actually absolutely not the case.
But is it also true that the increase in temperature will also make your spectrum harder?
No, but that it actually remember, it's not the temperature which increases, it's the flow which increases. The PT effective the temperature doesn't increase so much. It's really the flow. That's why we can measure the speed of sound. And if you look actually at the ratio of the spectra, and particularly if you do it with PID, you actually see the flow push. Okay. And not the hard scattering. So, I mean, I asked whether you also did the check, but this one should do more quantitative, because that is, of course, a potential source of confusion. And the other question I have, we measured many of these parameters, kinetic freeze out, chemical freeze out, average PT, and they are not so different in heavy ions than they are in PP. They are different on the level 10, 15, 20%, but not completely different by factors 2 or 3. So what would happen if you would just close your eyes and do the same analysis in PP? I mean, hopefully you would get completely crazy numbers, but that I would like to see. If you just say, I make the logarithmic slope in PT, average PT versus uncharged in PP, what numbers come out? They would even change with uncharged, but do they are in the same ballpark, 1/3, or are they completely crazy?
So I can't tell what will happen in PP, but I think one thing unique in heavy ion is that it first has to be flat and then take off.
No,
whether
this is your interpretation, and it all fits well, of course, with that. I just want to see whether in PP, if you don't start with a model but only with the data,
Yeah, right. So
just do the same thing. What do you get for your parameter, which is presumably not CS squared? But I just would like to see whether that gives roughly 0.25 of quarter or third, or gives a completely different number.
Okay.
Because you remember, we can do the same thing, and you don't have to argue whether there is kinetic freeze out or chemical freeze out in PP. You can just do the same analysis, and you get numbers which are 15% different.
So for clarification, do we have data at the moment, ultracentral high multiplicity PP, that we could plot similar to this, or we simply don't have?
No, of course it exists. I mean, it was measured. Remember, the thing looks grosso modo. Also, PT goes up with n charge. We know that since UA1, which measured that at the PB bar collider, and we have, I think, similar measurements. Also, we have even published that in.
But Jürgen, that's slightly different because here the x-axis is measured in the same. It's not done by an independent centrality estimator that's separated from the repeated.
Yeah, but you see, even if you don't do it well, if you do it with an independent centrality estimator, the way you do it, you get a precision which is order a few percent. If you would just do, even in this data, average PT versus average charge, even in the same acceptance, you would still get a CS squared, which is not very different.
So let's take it as a homework for us.
Yes.
So I don't know.
Just to see whether the ballpark is given by, I don't know, some lambda QCD or whatever, or whether this is really a unique measurement where only in heavy ions you get something which is anywhere close to a reasonable speed of sound. I think this would help me to place the result into the context.
But still, for me, it's first flat and then take off. This is a feature that I'm not sure whether this is a quite unique feature that I'm not sure that will also happen in PP. PP could be just monotonically increased. For me, that would be a sign of a different physics.
Yeah, it would be very interesting. I mean, Jürgen suggests that we're seeing this shoulder, this increase even in PP. It would be very interesting to take a look.
Yes, thank you.
So we'll take Cheming first and then Bernd. Cheming, please go ahead.
Yeah, thank you. The question related to what Uri Heinz mentions is to talk about the chemical non-equilibrium. I'm talking about entropy conservation. The quantum matter is quite viscous, therefore entropy is produced during hadronic evolution. Does your analysis depending on the constant entropy assumption or not?
So we will depend. So we need the entropy always proportional to n charge. So let's say if you during the hadronic evolution, your entropy always say change by some
But it increases because the resonant decay, so you produce more particles at the end. So in your analysis, the entropy it increases.
Let's say if you also always increase by 20% within 0 to 1% centrality, it will not matter because here we depend on the relative change of the charge multiplicity. Yeah, so basically.
Okay, fine.
It's a lot. So yeah, if the sum effect that change in entropy, very strongly depend on the charge, then that can matter.
But to be fair,
I do know that what happens is the entropy per particle during hadronic evolution, that is a constant. Entropy, baryon entropy per baryon, that's a constant. Entropy per particle is also almost constant. If you run SMASH, if you run URQMD, any hadronic afterburner, that's the result from the hadronic evolutions. Entropy does increases.
Yes, so
but increase with the increasing number of particles due to resonant decay.
And if the fraction that increase is more or less constant within this range, it will be fine.
Okay.
That's what I was saying. If for some reason it's not, then of course it can impact.
Yeah, but one can, in principle, do those hybrid model like Jones-Sense hydro 3 plus D, visco hydro plus afterburner. Then he can vary the results of the sound in the EOS, and to see what parameter can give the best fit to all the observables. That's another way of determining the speed of sound. Right.
Yeah.
So that I was puzzled by the other figure. I think the last figure of your slides, you have the hydro calculations there. Can you go to that slide in the end?
Go the end.
Yeah, that's one. That's right. That's right. Before that one.
This one.
Yeah, that's one. That's a hydro calculation, right? Hydro simulations. How can he only fix temperatures? They are meant the viscosity in the hydro through the equational state. It should have the velocity of sound of the whole shape of the nine-found lattice calculations, right? That's the input in the hydro calculations. So how can he only fix the 1 point?
Yeah, but still, this is still some hypothetical system.
Oh, using that hypothetical.
There's a mapping done in this nature space around the real system to some hypothetical system that is.
Okay, I got you. Yeah. So that you have to answer Bert Miller's question: is that how reliable is that assumption?
Right.
Okay, thanks. Anyway, yeah.
In principle, that's questions to not to me, to the series.
Yeah. Okay. Right.
All right, we can loop
Thank
back.
you. Yeah. Yeah.
Thanks, Jimmy.
All right, perfect. Bernd, do you want to ask your question?
Yeah, it's both a comment and a question. It is certainly tantalizing to see that a relationship between an observable and a fundamental property of the quantum plasma is in remarkable agreement with expectations based on a relationship that is, I would call, somewhat qualitatively motivated. And we have seen in the past decades that the system is more complicated than allowing in principle to make such one-to-one correlations. I mean, there have been efforts, I recall that about 10 years ago or 15 years ago, to determine precision values for the shear viscosity from a specific set of data. And we've learned that that is really not possible because there are other unknowns that also influence the evolution of the system, and you have to take into account the systematic uncertainties that come from those. And we've learned how to do that. So what you showed in, I think it's the previous slide, 24, suggests, no, it was not this one. No, also not that one, maybe 26, I forget. Yes, this one, right? Shows that the sensitivity of this particular observable alone is not as great as a few percent fit would possibly suggest. And so I would feel much more comfortable if we had a really good investigation based on current theoretical techniques of how sensitive the observables are, and not just one, but a set of observables, including this particular one that you have talked about today, to the equation of state of the quantum plasma. And in particular then, of course, there are other things that go into the equation of state than just the speed of sound, right? I mean, it has also a variety of other components, including the dissipative components. And so it is, I think we should not claim real success here and high precision before we have convinced ourselves that that we can really corroborate the conclusions in this more sophisticated and powerful way. So I'm just saying that as a warning, because we've learned that it is very easy in our field to make claims and statements that in the end come out as exaggerated.
Mm-hmm. Okay, thanks for the comment. Yeah, so there are actually there are more studies ongoing actually exactly in the direction you suggested to really understand.
Yeah, I think that's in the direction that it would be good if other groups would do that too, right?
Yes.
Because ultimately there are always limitations that go into each individual investigation, and before we can really claim a real measurement, we should have a broad consensus that the method is as powerful as we think it is.
Mm-hmm. Yeah, so we have to.
But you can be sure that both Atlas and Alice did the same and got the same. That
yeah, no, I don't think
it's nothing experimentally rated. So the physics correlation is the same and the numerical results are the same. The question is, are they the speed of sound or not? But
exactly right. I don't think it's a question of the experimental data. I think it's really a question of the theoretical interpretation. Mm-hmm. How cogent is that? How compelling is it?
We also started running, just mentioned the music plus URQMD model in parallel with Trajectum and also Fernando's model. There are multiple models being studied at the moment. Yeah.
Okay, very good. Yeah, I have follow-up questions about this, but I'll let other people ask their questions first. So Lorenzo, do you want to ask a question?
Hello, thank you. Thank you for the talk. It was very interesting. I would like to understand something about this interpretation. Could you please go back to the slide, what the effective temperature is not? Mm-hmm. So I just would like to understand the conceptual background that is behind this slide and this work. So you say I measure energy and entropy. Assuming that these are conserved because I evolve ideal hydro, for example, I can say I can integrate these things back and arrive at a hypothetical state. So this hypothetical state is a state that is static and is in global thermodynamic equilibrium, if I understand correctly. Mm-hmm. But that state never existed in the first place. So how do you resolve this? You say, okay, at the beginning, it was not expanding in the transversal direction, but it was expanding in the longitudinal direction. And assuming something like boost invariance, you can adjust for that and claim that you can map the true initial state, which is an expanding state, into an effective global thermodynamic equilibrium state. I mean, I just would like to understand how this idea of this effective thermodynamic equilibrium state comes about.
Mm-hmm. So wait, do you want to give it a shot? I know you meant, so Jean-Yves had to leave, and I know some people had to leave, so I don't know if you want to give it the shot or you want to defer to
many other people they want, but I don't know if Jean-Yves already left. Maybe
yeah, he told me he had to leave, unfortunately. Yes, and I don't know if Fernando could or Matt or Giuliano are still here.
I don't think any of them is here, so
yeah, yes. So I think you're going to back up.
I'll give a shot. Basically, I mean, our goal is to understand the equilibrium state of a hot QCD system, right? It doesn't have to be the system created in heavy ion collisions. Right? Our goal, if there's any system that would have, no matter how it's created, has a temperature of 200 something MeV, and if you can measure that system, that it will tell us about the equilibrium state of the hot QCD matter. So it doesn't have to be so. And your heavy ion collisions is one approach to create those type of systems. we create those systems and we take the energy to measure in those systems, and then based on then if we trust hydrodynamics, we convert that into a hypothetical system where we can determine the equinox state. That we can still learn about the hot QCD system, although it's not a system that was originally created in heavy ion collisions. But I think that's still.
I'm not sure I understand, because you have an energy and you have an entropy.
Yes.
And you are claiming that this
Alright.
energy and this entropy, apart from a volume, that are both proportional to a volume, and they are related by the equation of state. But these are the total energy and the entropy. And that it was said before, the energy carries flow. So it's not that
Yeah,
I
Lorenzo,
don't understand. Yeah.
We may have to follow up with the authors and
Yes,
away
yes,
separately for more information.
Although there's a flow at the freeze out, but all the energy come from the initial thermal energy, right? Right at the beginning, there's all the.
I think Lorenzo's point is that the medium is never a box, a static box, right? It doesn't
Exactly,
matter
yeah.
somewhere. It never is. But maybe we can follow up separately. Jürgen.
So it's now on a different feature, and that is the dip. The dip is unexpected. I don't see a direct hydro explanation of it. So that's just dip before the rise. It's in trajectum, but not in an analytical model. Has anybody started to think about what that could be? I mean, as long as we don't know where it comes from, we don't know whether it's interesting or trivial. So this would be another area.
I'll give you my thoughts, but I have no proof yet. I think it's a competing effect. You have multiplicity fluctuation, right? You can have a system of a fixed energy, but because of the multiplicity fluctuation, then if you sample the high end of multiplicity fluctuation, then the per particle energy will be lower, right? So if for fixed energy, and if you hit the high end of the multiplicity fluctuation, your mean PT will go down. But at the same time, when you require high multiplicity, you also sample system with higher total energy, and that drives the mean PT going up. So maybe there's a competing effect that.
Okay, then it's not obvious why it does show up in when centrality versus ET, but not in centrality versus and charge, because the effect should be in both. But I would also probably look into trajectum, where you can tune things, because that has it. So maybe there one can find out where it comes from.
That's a goal too. Yeah, we need some time to really change things to figure out what drives.
Just to find out whether that has information which is non-trivial, or if it's only fluctuation squared of n, it's trivial. But okay.
All right, sounds good. I'll allow myself one last question, even though we're past time. So if you go to slide 25 to follow up on Ben's question, so if we look at, my understanding is that the blue, and you can correct me if I'm wrong, the blue band is basically what you get if you take trajectum's mean PT, trajectum's charge hadron, you fit, and a similar procedure is what you do, and you get some extraction of the speed of sound. Is that what the blue band is?
Yes.
Right. So what we're seeing here is that we know exactly the equilibrium state is being used in trajectum, and we're certainly more than 10% off, actually. We're significantly off from the value. Now the value is included, but would it be fair to say that, given that trajectum's calculation includes viscosity, includes partization, includes everything, that would be roughly in a way, the theoretical uncertainty we can expect from this approach?
So in trajectum, what we found that the reason seems to be related to this point I talked about. When the uncertainty is based on a set of parameters that allowed by their Bayesian analysis on other observables. And it looks like the other observer can allow this large value of Q, larger than the TATB scaling. And that will, as I mentioned, effectively make your system smaller as you go to central, and that will contribute to a larger slope. So then the question is whether we can constrain. So if we can prove that we need a larger Q, yeah, this whole framework this argument will not be valid anymore. So the volume is not fixed. But my argument is that the Q, in principle, we have not looked at how their data compares our N-charge distribution, which is extremely precise. Now, I don't think if you change the Q, that a tail of the N-charge distribution should be very sensitive to that. So I would like to see if after we're constrained by the N-charge distribution, whether this large Q is still allowed.
I see. So in a way, we're moving towards maybe what Jan suggested, which is you need to add more. You may need to add more observable to get better constraints, and ultimately, maybe this will become. I'm sorry. Go ahead.
So that Q is not in other people's models. Everyone almost uses TATB scaling. And if you allow this Q to fluctuate to large number, was the main reason that their slope can get large. Right? I think we need more studies. But I'll have to see a better constraint of Q, if possible. Actually, Wilco is here. Right?
Well, I think I agree. Yeah, so makes sense. Yeah. I mean, the fact that we are at slightly higher temperatures is just that the mean PT of the charged hadrons is a bit higher. And this is a bit of an issue. I commented in the chat that we have a few more protons, like 10%, and that pushes our mean PT of the charged hadrons a bit higher than the pions, for instance, which fit much better. So okay, so that it doesn't fit exactly the CMS point. That might be an issue on like some recommendations of proton antiprotons. There are several complications why the horizontal point doesn't fit.
I see.
And yeah, I'm way about the height. Yeah, it's not only the Q. I mean, what's also very important is how you define the centrality. At least that's what we try to study in the paper. Like if you define centrality using uncharged or transverse energy, at least we find that also influences the slope, because transverse energy naturally leads to a higher mean PT because you're selecting on energy. So you're selecting a higher mean PT and you get a larger slope. This is okay, we need to study this further with Wei because they now also have these two centrality selections. But yeah, that also depends a bit.
Yeah, thank you, Wilke. Yeah, I mean, I think in the big picture, if the theoretical model is 20% accurate, maybe you've already reached what you can get from the CMS data, because CMS data is already more accurate than the model, possibly. So I think at this point, as many people said, it will be very interesting to see if models can better understand the accuracy of this formula, the effects that other models can play. And yeah. Well, if there's no more questions, thank you so much, Wei, for your time. You answered quite a few questions. Thanks everyone for staying. Thanks for the organizers for organizing this. And I don't know if there's any last word from Daniel.
Thank you, JF, for chairing our first, and we look forward to hearing from you later in the semester. So thank you, everyone. And we look forward to hearing from or seeing you all in 2 weeks for our next one.
Thank you. Thank you again.